And the next talk will be by Federico, and he will be talking about large eddy simulation on a marine turbine with stable stratification. Federico, maybe you can share the screen. Yes. All right.
Do you see the screen? Let me just set to full
screen.
Full screen. Yeah.
Perfect. Great. Take it away. Thank you.
Good afternoon to everybody. So the topic I will present today is about large eddy simulation of marine turbine under strong stratification. Partially is related to the work we are doing in area project together with the University of Sevilla and Valorant. Although in that case, we are working about reducer model for wind farm. So the modeling approach that I will show you today is strictly connected to the one that we are doing inside the area project, although here is the environment that is quite different. So the main idea is that when we have a wind farm, we extract as much as possible the available energy from wind. And recently there is a rising interest in doing a similar approach to the kinetic energy into the ocean and sea. And so inserting, let's say, marine farm to extract this source of kinetic energy. And in some way, the issue about this type of study are the same of wind farm. So to find a proper site with a good source of kinetic energy, and also the problem on how to optimize a possible marine farm. With respect to the case of AIR, so the wind farm, the condition of marine farm has a strong difference related to the density field, and in particular to the fact that during some period of the year, for example in summertime, or due, for example, to river inflow, the condition where the turbine are applied are subjected to a strong stratification. So we have a density field with a lighter flow in the upper part, and with a lower density in the upper part and higher density in the bottom part. And this can have a strong impact on the velocity and on the turbulent field. So if we want to optimize, for example, with a marine turbine, it is necessary, as in the wind farm case, to understand the behavior of the wake induced by this turbine to find the better global array to extract as much energy as possible. So there is an interest in evaluating the wake induced under the effect of stratification, but at the same time also to evaluate how the wake can impact on the stratification itself. And for example, within the sea, the wake could make a rise of sediment with an impact on the nutrients that characterize the water column. So the aim of this work is to start to have an idea on how stratification can play a role in this wake determination. And to do this, we are adopting a high detail model. So we are using a large eddy simulation. What does it mean? That we are solving here. There is the equation set that we are solving. So we have the continuity equation, the momentum equation, where the overbar represented the filtering that we applied to the Navier-Stokes equation. And because of this, we have a resolved Reynolds stress due to the grid size that we are implementing. And then here on the right-hand side of the equation, we are considering also a body force together with the viscous term and the buoyancy term that will be later used, for example, to apply an actuator disk model to represent the turbine. Together with these two equations, we solve also two transport equations, one for temperature and one for salinity. Also in this case, lambda represents the scalar flux related to the unresolved eddies of the grid. Then these two transport equations are linked in a two-way coupling with the momentum equation through the buoyancy term. So we have an equation of state for the density field that interact with the flow field and vice versa. Concerning the type of large eddy simulation that we are using, concerning the closure of the system in terms of the turbulence closure, we are using a classical eddy viscosity model that is based on the equilibrium assumption. So in mean, we are considering that there is not an increase of turbulent kinetic energy, and we are assuming that there is an equilibrium between production and destruction term. And here we are we introduced a eddy viscosity term that can be seen as the product between a length scale and a velocity scale, here expressed in terms of the strain rate tensor. And we are using a classical Smagorinsky model, so with a fixed coefficient that is set equal to 0.09. Why we are using a classical Smagorinsky model and not a more sophisticated one? Because the idea is then to move to more really applicative case with respect to the one that I'm going to show. And for example, a dynamic procedure for the computation of the constant could be problematic if you do not have direction of homogeneity. It can give rise to singularities. And then also because if we are going to deal with complex topography that can be, in our code, is solved with an immersed boundary method, it is not completely clear how the filtering procedure can interact with the immersed boundary. So we choose to use this simple approach. And then there is also another issue that make this C case to differ a lot from the case of wind farm. That in the case of C, usually the horizontal scale are much larger than the vertical one. And from a point of view of the computational cost, this usually results in a grid anisotropy with the cells that are much more larger in the horizontal direction with respect to the vertical one, with the aspect ratio that can be 1 to 10 or 1 to 15. And in this way, there is a problem because this length scale that appears in the eddy viscosity model tends to give a filtering that not necessarily this length scale, but tend to provide a filtering that act in all the direction in the same way. And so it tend to give rise to an anisotropic behavior of turbulence that becomes only a numerical artifacts and not a realistic representation of the physics of the problem. We have developed a model that takes into account this anisotropic question related to the grid, but it is not then used in the present case because we are simulating more a benchmark. Then, concerning the scalar transport, we are working on the Reynolds analogy. So fixing a Planck turbulent number equal to 1 and a Schmidt turbulent number also equal to 1. The second one is referred to the salt transport. And this assumption is correct if we are working with neutral or mild stratification. Maybe it can be improved when we move to the case of strong stratification, because in this case, buoyancy in the end act also as a destruction term when we make a balance of kinetic turbulent energy. But at the present time, we are not considering this issue. Just some information about the numerical aspect of the code is a finite difference code with a semi-implicit fractional step. So we use an Al-Bashford term for the explicit and the Crank-Nicholson for the implicit viscous diagonal term. The Poisson solver is a SOR with a multi-grid accelerator. And concerning the way we are considering the presence of the marine turbine inside the domain is with a blade element momentum. So, and then in the end with an actuator disk model with that take into account rotation. So going back to the previous slide when I showed the Navier-Stokes equation and there was a term B that represents a body force, it means that that body force within the model of the actuator disk acts as a sink of momentum. And so when we are computing the force acting on the turbine, this become a sink for the momentum in the equation. To avoid singularity of this body force that would be like zero everywhere and acting only in the area of the rotor, this is adjusted to have like a smoother distribution along the streamwise direction. And concerning the simulation, here there is a sketch of the domain that we are using. So the domain is quite coarse because we are taking advantage of wall layer model large Eddy simulation. So what does it mean? That if these are our domain with the marine turbine, at the bottom we are using wave function and so skipping the solution of the boundary layer. Then we are considering just a free slip at the top layer, and at the inlet condition we are providing fully turbulent field that comes from a precursor run. So we run the same case, but with a periodic condition on the streamwise direction, storing a plane of data of velocity, instantaneous velocity field, and then providing this as an inlet condition. This is computationally is a strong requirement, and This is also why it is useful to move from this case to reduced order model. But for LES is necessary because large Eddy simulation is not able to sustain itself if there is not an inlet of turbine kinetic energy. Another possibility would be to use synthetic a synthetic turbulence added to a mean profile at the inlet, but at the moment we are not working on this direction, also to make easier to then pass the model to as an input for a reduced order model. These are some preliminary tests concerning the actuator disk model. In this case, the test was for wind farm with respect to the work of Wu and Portugal 2011. And this showed the velocity profile between the large Eddy simulation, that is the orange line, together with the experimental results. These are the mean value along the some diameter after the turbine. So this is the incoming velocity profile, and then here you can see the effect of the velocity with respect to the experimental results. Then we start doing also some more related to the marine environment, some test case related to the work of Bayal 2007 in terms of the task coefficient and the power coefficient, in terms of their dependency from the tip speed ratio. Here the experimental results are with the square, and our results, the numerical results with the grid that then we are using for the other results are the red dot. We also try to see with a finite grid that is just for one tip speed ratio, with a finite grid, and we are obtaining very similar results. We try also with a coarser grid, but the results was very poor, probably because in this case with a coarser grid we were not able to solve the large energy carrying turbine scale. And concerning the test case, we perform first a case with neutral stratification, so a well-mixed water column in terms of density, and then two cases, one with a weak stratification and one with a strong stratification. The case with a weak stratification was set only in terms of temperature deficit, while with the salinity, that is the scalar that determine strong variation in terms of the density field, was for the strong stratification case. And here are reported in terms of the Richardson number that we used for the two cases that represent the ratio between the potential and the kinetic energy, or in terms of force, the ratio between the buoyancy force with respect to the inertial one. So here is the first case in which we set a neutral condition for the density field, and the marine turbine was set exactly at half of the height of our channel. And here you can see the development of the wake induced by our model, and how it starts to recover at several distance from the turbine, due to entrainment of the flow from the lateral, bottom, and upper surface. And here are plotted some surface just to give an idea on how the wake tend to extend in this case of neutral stratification. As we move to a weak stratified condition, we can start to observe several issues that develop in the wake after the marine turbine. It can be seen how the profile of the wake tends to be deviated toward the bottom, and just after for example, a 3 diameter after the rotor, it can be seen also how stratification tends to make the wake more two-dimensional than three-dimensional, because in the end, buoyancy act in avoiding the transfer of momentum from the horizontal to the vertical direction. And these determine also that if we consider a source of the kinetic energy, and this kinetic energy cannot be transferred in the vertical direction, it tends to spread on the horizontal direction, giving rise to the velocity field and also to the turbulent intensities. And here you can see also, still with some isosurface velocity, how there is this wake that is detected that start to be inclined. This issue is more evident if we pass to the case of strong stratification, where the wake deviation is pushed strongly toward the bottom, but here also other aspects start to develop. Having a density, because of the density field that we are considering, it tends to give rise to a two-layer flow with a higher velocity in the upper part and lower velocity in the bottom part. So in the end, because of the fit introduced by the actual disk model, it starts to rise a sharp interface in this velocity, and the faster fluid tends to enter the bottom. So here we have that the upper part of the fluid tend to enter in the bottom part, and then to give rise to other dynamics that can be seen in this case, that are not anymore related to the wake generated by the marine turbine, but to this flow that going into the bottom part of the water column give rise to the formation of eddies that give rise to momentum from the lateral and the bottom part to the vertical one. So this has an impact also on the density field, because in the end this became a large-scale mixing process. And for example, if here is the density field related to the case of weak stratification, here you can see how the density field, because of this turning of the wake and this eddy that is forming, tend to provide a stronger mixing of the density field and on the flow field. And this can give rise to some important thoughts about also the impact that can have on the environment, such type of wake for the suspension, for example, of nutrients. By the way, as a conclusion, what we understood from this type of simulation, that the stratified case in general have more energy production with respect to the neutral one, also because there is an increase of the horizontal velocity due to the buoyancy that inhibits the transfer of momentum and the vertical. There is also a faster wake recovery because as we saw, there is this downward of the toward the bottom of the wake, and also that the effect on of wake on stratification is stronger because of this rolling effect that is due by the faster upper layer that goes inside the bottom up. Thank you.
Very nice. Thank you. Very nice talk. Any questions? Any questions for Federico? Once again, okay, Thomas, yes.
Hello. It's nice to see you again, all of you, in particular Federico. Hello.
Yes.
So I have one question. Is in the case of strong stratification, you still use the standard Smagorinsky-Eddy viscosity formulation, no?
Yes.
Do you think that more adapted modeling could give different results, or?
Well, for sure, as I told at the beginning, in case of strong stratification, the Reynolds analogy start to be not so good, because I mean, Reynolds analogy works when we think that the eddies transfer momentum as the scalar, but this is not anymore true if we have strong stratification, because with the generation of internal wave, we can have a transfer of momentum, but not of the scalar quantities. So this is one issue. The second issue is that the strong stratification in the equilibrium assumption should be taken into account, because the destruction of kinetic energy is not only due to the viscous term, but also because of the buoyancy term. Yeah, at the present time, we did not. Maybe, I mean, if we take into account also this, the effect should be maybe stronger with respect to the one that I showed. I don't know if I.
No, I have really no idea what could happen. So I'm just asking. Okay, thank you. Thank you very much.
Thank you, Thomas. Any other questions from for yes, Simon?
Yeah, I don't know if you can hear me. Yeah, it's okay.
Yes.
Okay, thanks. So it was a very good presentation indeed. Very interesting results. I have a little question about the strong certification. Have you been able to validate the results you show us today by any measurements or theoretical bibliography or anything? Because this is the first time actually I see those kind of results, and this is very surprising for me. So I would like to go deeper indeed.
Well, the model that we used, for example, for turbulence was validated for the case of turbulent channel flow with stratification. For the case of the turbine inside the stratified case is a quite, I mean, is a topic that has not been so explored yet. So the test case that we performed was just on like a wind tunnel or tank experimental setup, but not in the stratified case. But I mean, the model that we use in general has been validated also for the case of stratification.
Okay, thanks.
Thank you, Simon. Maybe in the interest of time, we should move on. Thank Federico again. Thank you, Federico, for the very nice and interesting talk.